Section 1. A Whisper from the Void. A Change in the Path of 3I/Atlas. Tonight let us talk about a quiet and subtle message from the cosmos. The magnificent James Webb Space Telescope, our new eye on the universe, has been observing an object passing through our solar system. This celestial traveller has been given a designation 3I/Atlas. As Webb watched, it detected a very small yet significant deviation in the object's path. Visualize that small trajectory shift, a tiny bend in the path. Some headlines, ever hungry for alarm, might frame this as a terrifying development. It is nothing of the sort. It is in fact profoundly interesting. It is a clue whispered across the void, a delicate puzzle box delivered to our doorstep, a rare opportunity to learn. In these moments it is our responsibility to meet the universe not with fear, but with curiosity and a calm, rational mind. The change in the trajectory of 3I/Atlas is not a harbinger of doom, it is a scientific observation of immense value. It tells us that this object is not merely a passive piece of rock coasting through space under the pull of gravity alone. Something else is happening. Some other more subtle force is at play, gently nudging this visitor as it feels the warmth of our sun for the first and only time. This essay will serve as your guide, explaining precisely what has been seen, what it means, and why it inspires a sense of wonder, not dread. We shall proceed with clarity and without hyperbole. The universe is dramatic enough on its own terms. It requires no embellishment. Understanding the James Webb Space Telescope. To comprehend the discovery, we must first appreciate the instrument that made it possible. The James Webb Space Telescope, or JWST, is one of humanity's most ambitious scientific creations. It is not like the telescopes you might be familiar with on Earth, nor is it a simple successor to the Hubble Space Telescope. Webb is a specialized observatory engineered to perceive a form of light that is invisible to the human eye. It sees the universe in the infrared spectrum. Think of infrared as the light of heat. Everything in the universe that has some warmth, even if it is incredibly cold by our standards, emits a faint infrared glow, and Webb is designed to capture it with breathtaking sensitivity. This capability is its superpower. By looking at infrared light, JWST can peer through the vast clouds of cosmic dust that obscure the view of other telescopes, revealing the birth of stars, revealing galaxies that were previously hidden. It flies far from Earth, 1.5 million kilometers away, at a special point in space where it can remain cold and stable. Its giant gold-coated mirror, over 6 meters across, acts as a colossal light bucket, gathering the faintest whispers of light from the most distant corners of time and space. It is this extreme sensitivity that allows it to perform measurements of astonishing precision, tracking the position and properties of a small, dark object like 3I/Atlas. A primer on interstellar objects. The vast majority of comets and asteroids we see in our skies are locals. They were born in our solar system Earth, other planets gravitationally bound to our Sun, destined to circle it for billions of years. An interstellar object, however, is something else entirely. It is a tourist, a wanderer from a different star system unbound by our Sun's gravity. These objects are on a one-way journey. They fall in from the depths of interstellar space, swing once around our Sun on a hyperbolic orbit, then head back out into the galaxy. They are messengers from cosmic shores we have yet to explore. Until recently, the existence of such objects was purely theoretical. That all changed in 2017 with the discovery of one I/Oumuamua. This name is Hawaiian for a messenger from afar arriving first. Oumuamua was strange. It was small, elongated, moving incredibly fast. It showed a slight acceleration away from the Sun that could not be explained by gravity, yet it had no visible tail of gas or dust, like a typical comet. Let us now focus on our current guest, 3I/Atlas. In the simplest of terms, it is a small body rock ice journeying through our solar system. Based on its brightness, astronomers estimate it to be relatively small, perhaps a few hundred meters across. To put that in perspective, imagine an object the size of a large city block, a modern skyscraper tumbling silently through the vacuum of space. The term orbit shift can sound quite dramatic, perhaps conjuring images of a celestial body suddenly swerving onto a new and dangerous course. The reality is far more subtle and, frankly, far more common in astronomy. An orbit is simply the path an object follows under the influence of gravity. When we first discover an object, we only have a few data points, and our prediction of its future path has a degree of uncertainty. Think of it like drawing a line through a handful of scattered dots. There is some wiggle room. An orbit shift often just means that as we collect more data, more dots, we refine our line, making it more accurate. So, why would an object's physical path deviate from a purely gravitational one? The most powerful force governing celestial motion is gravity, Sun, Jupiter. Other planets' 3I/Atlas's trajectory. However, other more delicate forces can also act upon a small body, especially a cometary one. One of the most likely culprits for the observed shift is a phenomenon known as outgassing. As this icy body gets closer to the Sun, its surface warms. This heat causes frozen gases like water, ice, carbon dioxide, ice to sublimate, turning directly from a solid into a gas. This gas then erupts from the surface in jets. These jets of gas act like tiny, natural rocket thrusters. According to Newton's third law, for every action, there is an equal and opposite reaction. As a jet of gas shoots out in one direction, it imparts a gentle but persistent push on the object in the opposite direction. If these jets are not perfectly symmetrical, they will produce a net force that nudges the object off the path that gravity alone would dictate. This non-gravitational acceleration is a well-known phenomenon observed in many comets within our own solar system. The tiny shift seen by JWST is likely the signature of this very process occurring on our interstellar visitor. Another, even more subtle force is solar radiation pressure. Sunlight itself, composed of particles called photons, carries momentum. It is an unfortunate reality that fear sells newspapers and generates clicks. A headline proclaiming a terrifying orbit shift is designed to provoke an emotional response, not to inform. It is crucial that we resist this temptation for alarm and instead look at the situation with calm, factual analysis. The risk associated with an object like 3I/Atlas is a matter of quantifiable numbers, not scary adjectives. The first and most important fact is that space is almost unimaginably vast. Earth is, by comparison, a microscopic target in a cosmic ocean. The probability of any given interstellar object happening upon a trajectory that intersects with our planet is exceedingly low to begin with. Let us be perfectly clear, the observed orbit shift for 3I/Atlas has not moved its path closer to Earth in any meaningful way. In fact, such shifts, when they occur, often move the predicted path further away from a potential collision course. We are tracking this object with immense precision. If there were even a remote possibility of a threat, you would not be hearing about it from sensationalist headlines, but from a unified, sober announcement from the world's space agencies and astronomical organizations, such as NASA and the Minor Planet Center. To put the risk into perspective, consider everyday activities. The statistical risk you face from cosmic impacts is far, far lower than the risks you accept daily. While many telescopes can track the position of 3I/Atlas, the James Webb Space Telescope brings a unique and irreplaceable set of tools to the investigation. Its power lies in its ability to do more than just pinpoint the object's location. It can dissect its very nature. As 3I/Atlas is warmed by the Sun, any ice on or just below its surface will turn to gas, and this gas will glow faintly in infrared light. Webb's spectrographs are exquisitely tuned to pick up these faint emissions and identify the chemical fingerprints of the molecules responsible. This is how we can learn from over 100 million kilometers away if the jets pushing the object are made of water, carbon monoxide, or something more exotic. This chemical analysis is the key to unlocking the secrets of the object's origin. The relative abundance of different ices in a comet acts as a sort of birth certificate, telling a story about the environment in which it formed. Webb, operating in the cold, clear vacuum of deep space, provides a pristine window into the chemistry and physics of this interstellar visitor, revealing details that would otherwise remain completely hidden from us. The story of 3I/Atlas is far from over. In many ways, it has just begun. The detection of this subtle orbit shift is not an endpoint but a catalyst for more science. In the coming weeks and months, astronomers around the world will continue their vigilant watch. Ground-based telescopes steady stream of positional data, narrowing the cone of uncertainty in its trajectory. Continuous tracking provides the long-term baseline, while Webb gives detailed snapshot observations. Every new data point strengthens the orbital model and makes predictions more reliable. Next, more observation, more calculation. Teams will model non-gravitational forces in detail, chemical data from JWST to inform what gases are driving the jets. By combining all of these puzzle pieces, they can build a comprehensive simulation. This entire episode is a spectacular demonstration of why we explore. This is not about fear, it is about wonder, curiosity, and the profound satisfaction of understanding our place in an infinite, magnificent cosmos.